All right, guys. So what we're going to be looking at today is integration with exponential functions. And this is lecture 5 here. So this is a nice, easy topic, so you'll be happy about that. We've got some difficult ones coming up pretty soon, but this one is not difficult, right? But it is the first time we're going to be doing integrals this semester, and so you have to remind yourself of how to do those. So I'm going to spend a few minutes doing that. Reminder of how integration works, right? I'm not going to go into great detail, but just a couple, silly examples just to make your brain work again. So you know about derivatives, right? So derivatives. Here's an example. If you take the derivative of x cubed, you get 3x squared. Of course you know that. And if you take the derivative of, let's say, tangent x, then the derivative of tangent x, hopefully you'll remember, is secant squared x. Okay? Now you know those. Every derivative formula, though, is an antiderivative formula. So the same formulas as antiderivatives look like this. So the same info, but as an antiderivative formula would look like this. So an antiderivative, another way to say antiderivative is to say an indefinite integral. So the indefinite integral of this side with a dx thrown on the end is equal to the other side, x cubed, and we need a plus c. So that goes there, that goes there. Okay? And there you go. So an antiderivative is undoing a derivative or working backwards. So for this other one, an antiderivative of secant squared x dx is going to be tangent x plus c. And just like before, that one goes there, that one goes there. Okay? And that's just a really, really basic reminder of what an antiderivative is. There's also what they call definite integrals. So you're going to have to do some definite integrals as well. And so you want to remember the fundamental theorem of calculus, right? If you don't remember that, you should feel bad. It's the fundamental theorem of calculus. No, I'm just kidding. What is it though? We should know it. I'm just kidding, but no, I'm not kidding. The fundamental theorem of calculus. All right. So what is it? So it says this. Well, there's more than one form of it, but of course there's more than one form of it. It's called the fundamental theorem of calculus, so of course there's more than one. But the fundamental theorem of calculus is basically this. If you have an integral from a to b of little f of x dx, don't ask me why the integral symbol is so huge. What you do is you, number one, find an antiderivative. Which we typically denote as capital F. And you want to evaluate that between A and B, which means the top number you plug into the big F, and the bottom number you plug into the big F. And that's the fundamental theorem of calculus. Now, how do you use it? Well, it's not hard, right? So here's an example. Let's say I have from 0 to pi of x squared plus cosine x dx, right? And you want to evaluate that. So your first step is find the antiderivative. Not derivative, antiderivative. I'm going to post a thing of common integrals and derivatives for you on the page. I'm going to link it in, what is it going to be? I'm going to link it in the notes and videos for week 2 page. So look in videos and notes, I think it's actually called, for week 2 for a link to common derivatives and antiderivatives, just as a PDF. Derivatives. All right. So let's do this. So we need an antiderivative here. So you have to remember the power rule for x squared. And the power rule is not the power rule for derivatives, it's for antiderivatives, right? For derivatives, it looks like this. The derivative of x to the n is nx n minus 1. The antiderivative of x to the n is the opposite. You add 1 to the power and you divide by the power. And plus c, but I ran out of room. All right, so let's do that. So if you apply the power rule to x squared, you add 1 to the power and you divide by the power. Okay, now you need the antiderivative of cosine x. Now, remember, it's the antiderivative of cosine, not the derivative. The derivative of the cosine function is negative sine x. The antiderivative of cosine is positive sine x. Why is it positive sine x? Because take the derivative of sine x. What do you get? You get cosine, right? So the derivative of positive sine is positive cosine. So this is the way the signs work, because you're working backwards. And then these limits of integration, as they're called, put them there. Now, after you have that, your second step is you have to take those limits of integration and plug them into the function. So you put the pi in here, you get pi cubed over 3 plus sine pi minus, and then you put the 0 in here, 0 cubed over 3 plus sine pi. And then you just work that out. So typically on the homework, you have to give an exact answer. So you don't punch this into a calculator or anything like that. We just need to evaluate this by hand. So pi cubed over 3 is just pi cubed over 3. Sine pi, well, that's 0. Then minus 0 cubed over 3, that's 0. And then minus sine pi. Sine pi is 0. Whoa. Why is it sine pi? Why sine pi? That's wrong. Right? We're supposed to be plugging in 0 into that function. Should be sine 0. Okay. Sorry about that. So 0 cubed over 3 is 0. And then minus sine 0. And sine 0 is also 0. So when you work it all out, third time's the charm. You get pi over 3. Okay? And that's the fundamental theorem of calculus. So none of that was exponentials at all. Okay? But that was just a reminder of very basic integration. Okay? Now let's actually look at today's topic. So today's topic is actually exponentials. So integration for exponentials. Exponentials. Sound it out? use your phonics, we can spell it. All right, what's going on here? So just like I did up here, right? I wrote some derivatives and then I rewrote them as an antiderivative. We're going to do the same thing here. So in the previous lecture, we learned these derivatives. We learned that the derivative of e to the x is e to the x, nice and easy. And we also learned that the derivative of a to the x, where a was not e, well, even if a is e, it works. But the derivative of a to the x is a to the x ln a. Okay, so we learned those derivatives. So those are derivative formulas. But you can write them as antiderivative formulas. Okay? And those are the ones that we actually want. So just like we did up here, right? So look at this. So the derivative, right, ends up over here, and the antiderivative ends up over here. Wait, what? No. The one on the left ends up on the right, and the one on the right ends up on the left. That's what I want. That is what I want. Let's get rid of these. Okay, so as an antiderivative formula, right, if this one comes left and this one goes right, then you're going to have the antiderivative of e to the x dx is, what is it? It's just e to the x. No, what? Plus c. Okay? And the same idea for the other one here. So we have also the antiderivative of this one, a to the x ln a dx, should be equal to the one on the left, which is a to the x plus c. However, we don't really like writing it this way. So the way you're going to want to remember these formulas is as follows. So the first one's fine. The antiderivative of e to the x dx is e to the x plus c. Perfectly fine. On this one, this ln a is usually not going to appear in your integral. And so we would like it to be on the other side. Now the way you make it go on the other side is you just divide both sides by ln a. So when you do that, you're going to get this formula. And I'm not going to, show it just because you don't really need to use it. I mean, you don't really need to derive it the way that I am right now. You just need to know it. Okay? And so here's your formulas for integrals of exponentials. And I actually think that, why is it doing that? I don't know. I actually think that it doesn't even use the second formula in your homework anyway, so I don't think it's going to matter. But those are the formulas, okay? And so the way you're going to see them in the homework is, at first, you're going to see just very easy antiderivatives to get you used to doing antiderivatives. So there's 3 types, I think, of problems in homework set. I was going to number it, but I didn't number the homework, so I'm just going to say in the homework set. So the first type is easy. So first type, just e to the x somewhere. That's all. So you'll see that like this. Like, here's an example. Integral 2x to the 6th minus 5x to the 4th minus 2x cubed minus 4 plus e to the x dx. And by the way, I just noticed that this says on the homework on Newton, which they start with a K because they don't know how to spell. On Newton, they say no plus C. Now, of course, to be correct, you need a plus C in your answer. I'm just pointing out that the online homework does not want it. And that's just for the homework system. Okay? It's not a math thing. All right, so let's do it. We should just be able to write our answer. So all we're doing is just for this, 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 and this, we're just writing separate antiderivatives. So the antiderivative of 2x to the 6th, we already talked about it, it's power rule. Add 1 to the power, divide by the power. 5x. Same thing here. Add 1 to the power, you get 5. Divide by the power over 5. Minus 2. X cubed, so we add 1 to the power, get 4. Divide by the power. Minus 4. The antiderivative of 4 is 4x. And finally, we get to our e to the x. What's the antiderivative of e to the x? Well, it's right here, right? The antiderivative of e to the x is just e to the x. Very easy. So, oops. So what's the antiderivative of e to the x? Just e to the x plus c. That's your answer. Okay? So that first type, there's really nothing to be seen other than what we just did. And so your homework will have you do, handful of those, 3 or 4 of those. But they're not tricky. They're easy peasy. What else is there? I lied. Your homework's going to make you do like 5 of them or something. So what's next? So the next thing that they're going to make you do is they're going to make you do problems that have either substitution in them or a shortcut. Okay? So we need to know integration by substitution. Now that's something that they teach in Math 4A. Okay, integration by substitution. Now I'm going to show you an example that actually is not even an exponential at first, just to show you something. Okay, so here's an example of substitution, no exponentials in it. So let's say I want to do the integral of, let's say, x cosine x squared plus 1 dx. All right, so that's a very straightforward integration by substitution problem. Okay, so what you're supposed to notice about this is, number one, you don't know the antiderivative off the top of your head. Okay, you need to recognize that. Okay, it's not a super easy look at it and know the answer problem. I mean, I guess some people do, but generally speaking, you're not going to know that. Okay, so you need to recognize that and not try to integrate. Like, you don't do antiderivatives of x and cosine and x squared. You don't do those all separately. That's not the way integration works. Okay, you need an appropriate technique here. So you notice that. The next thing you want to do is say it's probably substitution, because that's the only advanced technique we know right now. So if we want to try substitution, you want to let u be the inside function, okay? Inside function. Inside what? Well, inside another function. So if you look at what we have here, you should realize that this part is inside of the cosine function. So that's your inside function. So when I say let u be the inside function, I mean let u be the inside function, which is x squared plus 1. Okay? Now once you have that, you need to take the derivative of what you just wrote. I'm just going to say your substitution. Okay? So I have u equals x squared plus 1. I'm going to write this middle step here. Du dx equals, and then you need the derivative of x squared plus 1. So the derivative of x squared plus 1 is 2x. Okay? Now, a lot of people, they don't write this. They won't write that. What they will write is this thing, but if you move the x up, so they'll write this instead. Du equals 2x dx. Okay? So if you take 2 lines to do it, that's fine. If you do it from here to here, that's fine. Okay? So you take the derivative of your substitution. Now, what you want to notice is that in your original integral, you don't have a 2x dx. Okay? In your original integral, you have a dx and an x. Right? What I mean is this. So you've got a dx here, and you've got an x here. Okay? And here you have an x and a dx. But this 2 is extra. So it looks like there's an extra 2. Move it over to the other side. All right. So we're going to have du divided by 2 equals x dx. All right. And this is what we want to have. So let's just take stock of where we are here. So we have this x squared plus 2 in the function, and x squared plus 2 is actually u. All right? And then in the function, we have the dx and the x, but here's the x dx, that's the same thing. And, oh, sorry, here. There's the x dx, and it's equal to du over 2. So the 2 things that I highlighted there are what our substitutions are going to be. So now you make your substitution. So our integral was x cosine x squared plus 1, I think it was, dx. But I'm going to move this x to the end. That's the same integral, right? Integral cosine x squared plus 1 dx. All right, so we want to make our substitution, but x dx right here, that happens to be equal to du over 2, right? It's right here. And the x squared plus 1 happens to be equal to u. It's written right here. All right, so our integral becomes the integral of cosine u du over 2. Okay, or if we take the over 2 and we move it out of the integral, like that. Okay, well now the integral suddenly looks a lot simpler than it did. So now we can try to integrate. So we've got 1/2 integral cosine u du. Well, what's the antiderivative of cosine u? It's sine u, right? How do we know that? Well, I think we did that at the beginning here, right? Didn't we? No. Yeah, we did one right here, right? Antiderivative of cosine is sine. Oops, back to the bottom. So the antiderivative of cosine u is sine u. And then u was made a variable, so we have to substitute back to the original variable. Okay, and when we do that, we're going to get 1/2 sine u. But what was u? I'll come back up here, right? You've got your substitution right here. U is equal to x squared plus 1. So come down here, u is equal to x squared plus 1 plus c. And that is going to be your answer there. Okay, and so that's the method of substitution. What can we say about that? Yeah, right, so that's the method of substitution. Now, how are we going to apply it to integrals with exponentials? Well, I'm actually not. I'm gonna give you the punchline here. Okay, so if you use substitution, you can find the following. So these are going to be like shortcuts to save you from having to do that same kind of substitution on every single problem here. So here's one of them. So we know this, right? So I'm going to write this. We're starting with this. We know that the antiderivative of e to the x is e to the x plus c. Okay, we know that. What if it's e to the kx? What's going to happen there? Where k is a number. Well, it turns out that what's going to happen is you're going to get 1 over k e to the kx plus c. All right. Now, what if I have this antiderivative, e to the kx plus b dx? Well, it turns out that that is going to be 1 over k e to the kx plus b plus c. And this is assuming, all of this is assuming that makes me sad. Okay, there we go, better. All of this is assuming that k and b are just constants, okay? So assuming, hey, stop it. K and b are constants, okay? So if you use those rather than doing substitution, then you're going to have an easier time with some of these problems coming up. So like here's an example of one where you could do substitution, but if you know the formulas above, you'll save some time. So -2 to 0, integral -7 e to the, I'm going to say 6t minus 3 dt. All right, so the integral is a t integral instead of an x integral, you know, who cares? So this is a definite integral, right? So this is definite, and it's a substitution integral. Except, like I said, we're not doing substitution because we're cheating. Not cheating. We're using a previously discovered formula. Okay, so how are we going to do this? So we're going to find the antiderivative. Okay, well, we have a formula for the antiderivative right here because this is in this form, right? Which is that form. And this is our answer for the antiderivative. So all we're going to do is we're going to say, well, the -7 there is just along for the ride. But what's the antiderivative of the part that I highlighted? Well, it's going to be 1 over k. The k is 6. And then e to the whatever. E to the whatever. Like that. Okay, so that's my antiderivative. And you would have had to use substitution. If you check the book, they're going to make you do substitution. Now this is what's it called? This is a definite integral, so we still have these limits of integration to worry about. Okay, so we have the antiderivative, but now we need to worry about our limits of integration. So now, let me just actually erase that. Put over here because we're going to need more space. So then what you're going to do is you're going to take the 0 and you are going to plug it into this formula and get -7 over 6 e to the 6 times 0 minus 3. Right, there's the 0, that's that 0. And then you've got a -2 down there. So minus, and then you're going to plug a -2 in. So -7 over 6 e to the 6 -2 minus 3. Where that's that. Okay, so that is your fundamental theorem of calculus. Now, what do they expect you to do for a final answer here? Well, they just expect you to do kind of the barest minimum of simplifying these two exponential terms. It's almost nothing. So you just have to say, well, 6 times 0 is 0 minus 3. So that's -7 over 6 e to the minus 3. And then you've got a minus. Hey, no, why? You have a minus. So a minus is a plus. So plus 7 over 6 again. And then it's e to the, well, what's the exponent? 6 times -2 is -12. -12 minus 3 is -15. And that's it. That's what they expect. The only thing you might do is you could take out a 7 over 6. And if you take out a 7 over 6, I'm going to write this one first because it's positive, e to the -15, minus, the other one is e to the minus 3. So if you wanted to, you could write it that way. The previous answer should have been fine though, so you don't have to do too much. All right, so that's how you do it, okay? So technically it was a substitution integral, but we took less amount of time to do it just because we knew that boxed information there. Okay. All right, so we got, I think, one more type of problem on here, which, I mean, I know what it is. I don't know what I'm looking at. So it's just a type where you can't avoid substitution. So the last type, substitution, and we can't avoid it. Substitution. What can I say about it? And we can't avoid it. Unavoidable. All right. So what's that look like? So that really looks a lot like that cosine problem that we just did. So it'll be like an integral. There's something here that you can't get rid of. So I'm going to say like, let's say like 4t, I don't know, 6. 4t to the 6th. And then you're going to have something like e to the something. The something needs to be 1 degree higher. So I'm going to do 2t to the 7th dt. So that's going to be the type where we can't avoid substitution. Okay, so you recognize that this is not one that you know the answer to, right? So we need substitution. You need to realize that you don't know the answer and that we need substitution. Now, just like before, you need to identify the inside function. So the inside function is here. That's the inside function, okay? So your inside function is u. So you say let u equal 2t to the 7th. Then what do we do next? Take a derivative. I'm not going to write every step. Du equals, take the derivative. What's the derivative of 2t to the 7th? 14t to the 6th. And then we have a dt. All right? Now what you should recognize here is that you've got a t to the 6 and a dt. And down here, you've got a t to the 6 and the dt. But you also have a 14, right? You've got this 14 here that you don't need. So you move the 14 over to the other side. You move the 14 to the other side, and you have du over 14 equals, not 14, because we just moved it, t to the 6 dt. Okay? So then what you need to do is just replace this and also this, right? So 2t to the 7th is u, and 6t dt, sorry, t to the 6th dt is du over 14. So you make your substitutions this way. So what are they going to look like? Integral. What happens to the 4? Nothing, right? We're not doing anything to the 4. They're just carried along for the ride. Then you've got, well, actually, I'm going to do this in an extra line. Hold on. 2t to the 7th, t to the 6th dt. Okay. And then that way we have the t to the 6th dt there, and we have 2t to the 7th there. All right, now let's do this. So the 4 is just a 4, write it. Then we have e to the 2t to the 7th. But 2t to the 7th, we know is u. All right. Then we've got t to the 6th dt. But we know that t to the 6th dt is du over 14. So you have that. So take the 4 and the 7, take the 4 and the 14 out as 2 over 7, and you have the integral of just e to the u du. Well, now you do your antiderivative. And it should be easy now, right? What is the antiderivative of e to the u? Just e to the u plus c. Okay, good. Now, to get your final answer, you need to substitute back to the original variable. So the original variable was the t's. So you go back to your substitution and make the substitution for the u there. So u is going to be 2t to the 7th. So, whoa. See. All right. So replace the u with 2t to the 7th. So you're going to have 2 over 7 e to the 2t to the 7 plus c. And that is going to be your antiderivative. Well, hold on. Should not have that. Okay. All right. So that is my answer there. So that's how substitution looks when you're not writing a bunch of extra steps and explanation. Okay. If you need more help, come to my office hours. There are a few people who come to my office hours and just kind of do homework. One of those people could be you. All right, so that's it for right now. Good luck on your homework. More videos are coming up. Stop.